In this video, we're going to be covering the starting system. Components make up the starting system. It's going to be the battery. You need to make sure that you have a good battery before you start looking for a starting system problem. Cables and wires. Again, you need to make sure the cables and wires are in good condition, not the corrosion going on there or loose connections. We're going to be looking at the ignition switch, the starter solenoid, which is this part down here, which is also a relay. Keep that in mind, that the starter solenoid is also a relay. Looking at the starter motor, which this gives a simplified one. Starter drive, which is also referred to as a pinion or a bendix. The ring gear, which is going to be on a flux plate or the flywheel. And then your safety switch, which will be different for a manual and an automatic transmission. Components that make up the DC motor. Armature, this part up here at the top, which includes the commutator. You need to keep in mind that the commutator is part of the armature. This is the part that the brushes are going to ride on. These are your brushes down here. Brushes are going to be held stationary. Armature is going to be spinning, and that's what the pinion drive is splined to. Field windings, you can see these wires here. Down here, you can see just a little bit of it. This is going to be coming from the motor terminal of the starter solenoid. That's going to bring your battery voltage in. Current's going to flow through the 4 field windings. The section on the inside, this is your soft iron core, which makes your magnetic field much stronger. They're going to call that a pole shoe. If you don't have the field windings, what the manufacturers have gone to now is using permanent magnets on the outside. You have the armature with the commutator, the housing, which has the field windings and the pole shoes on it, and the brushes. Armature has 2 different designs, a lap winding and a wave winding. This is academic. For you, if you're working on it, to test these correctly, you have to have a tool called a growler. They're expensive. You can test it with an ohm meter, but whether you're using a growler or whether you're using an ohm meter to test them, you test them exactly the same. So it's the engineers that design the motor that are going to choose which one of those they want. Field windings. This is the other side of that same motor. So this is the lead coming in from the M terminal. Current's going to flow through all 4 field windings, and you only see 3 of them on here. And then it's going to come out to this terminal and this terminal, which on this motor is broken. These are going to go to your brushes out here. This is your brush here, so I use this one because there's 2 different designs here. You can see that this has an insulator on this brush and on this brush. These are going to be your hot brushes. This connection right here would go to these 2 terminals, feed to your hot brushes. Current's going to go through the armature, then to the 2 grounding brushes. This metal plate right here, which is your brush holder assembly, is going to be screwed to the housing, which the housing of the starter is ground. This is another style over here. You're looking at the bottom side here. This is the insulated brush where it's going to go, and your grounding brushes. These circle things right here are actually springs. That's what push the brush out to hold it tight against the commutator. 3 different styles or types of motors. First one is a series. On this one here, this is our series. Current's going to flow from this post here. This is coming from the motor terminal of the solenoid. It's going to go through this winding, this one, this one, this one. So your 4 field windings are wired in series. Then to your 2 positive brushes, through the armature to the 2 grounding brushes. The second one is shunt, and this is actually the primary reason that I'm talking about this. You need to remember the word shunt. If you have a shunt circuit, a shunt gauge, all that means is that something is wired in parallel. As long as you can equate that when you hear the word shunt, it means parallel, you'll do fine. Here's coming in from our M terminal, but this time it's going to come this direction through 2 of the windings, this direction through 2 of the windings, joined together to the 2 positive brushes, so we have them wired in parallel. This one is compound. The only time I've ever seen a compound is you go back to the 60s. Ford was using a different style of starter motor that had this compound. You can see on this one, current comes through this winding and then directly to ground. These 3 are wired in series. That's the reason they call it a compound. Again, it's academic. When you're testing the field windings, you're going to take an ohm meter. You're going to check from here to your 2 positive brushes. You should have continuity. You're going to check from here to the housing. There should be no continuity. You're going to do a visual inspection to make sure they haven't been scraped against, that the insulation isn't gone off of there. The visual inspection is good. If the continuity is good from this post to your two hot brushes, no continuity between here and the housing, you're good to go. It doesn't matter which type, whether it's a series, a shunt, or a compound. Last one of the motors, and this is a permanent magnet motor. This one we looked at earlier. They're going to call it a PMGR. The permanent magnets don't have as strong a magnetic field as the electromagnets do. Permanent magnet starter motor will always be a gear reduction motor. Up here, I'm showing you the two images. Here's a starter motor, and here's the PMGR. They're smaller, they're lighter, which is the reason the manufacturers have gone to them. They'll say that they're about half the weight. What the manufacturers want to do is get rid of weight on the car. The less weight there is on the car, the better fuel economy you can get. Planetary gear set is the way that most of them achieve their gear reduction. You can see this here. Here's our armature. Armature is going to be the sun gear on this. Ring gear is held in place. Planetary gears are where we're going to get our gear reduction to turn the pinion drive. Typically, they're going to be about a 3-to-1 gear reduction. That means the armature is going to turn 3 times for every 1 time that the pinion drives, and that's our torque multiplier. This one we're going to try to quickly explain how a DC motor works. Hopefully you can catch this. If it doesn't make sense what I'm talking about here, do a YouTube search for DC motor, how it works. You'll get a bunch of different videos, and this particular one I thought gave a good explanation. Looking over here, this blue piece here and this blue piece here are 2 sectors of the commutator. Here's our commutator. This is 1 sector of the commutator right here. What they're doing is taking just this one and then 180 degrees off. They're taking 1 over there. They're just going to show you 1 loop that's on here. You can see by looking at this, there's dozens of loops around there. Looking on this one here, you can see they're wound around like this. This is the part that's actually going to be magnetized. This right here is going to be our electromagnet. We're going to have a brush. So looking at this one here, we have the brush here, 180 degrees. We have the grounding brush. So we're going to be touching here. 180 degrees, we're touching over there. This one is our hot brush, grounding brush. So current comes in from here. Current's going to flow through this and then to ground. Anytime you have current flowing through a wire, you're going to have a magnetic field around there. Talked about the right-hand rule of thumb. Current's flowing in the direction of your thumb. Magnetic field will be in the direction of your fingers. We have it coming from the commutator up to this end here. Then it comes the opposite direction. Because it's coming the opposite direction means the magnetic field is going to be in the opposite way. We have our magnet over here. Whether it's an electromagnet or permanent magnet, doesn't matter. We're going to have a magnetic field. This is going to interact, and it's going to push this in a clockwise direction. If all you had was 1 winding, this would only turn until this was straight up and down, and then it would stop. They're going to have multiple, like this over here, so when the one gets to the top and is no longer being pushed, there's going to be several others that are still being pushed. As it comes around to the other side, if the magnetic field stayed the same, it would push against it. But what's going to happen is this sector is now going to be touching this grounding brush, whereas this sector of the commutator is going to be touching the hot brush, which means the current is going to reverse through your armature. If we look at this side here as an X, and this side over here is a Y, current flows from X to Y. When this comes 180 degrees, Y is going to be over here, X is going to be over here, so current would flow from Y to X. Each time this makes a 180 degree rotation, we're going to reverse the current flow, meaning we're going to reverse the magnetic field. But this turned 180 degrees, so when we reverse the magnetic field, we actually kept it pushing in the same direction. Here's our commutator, multiple different sections. That's what's going to keep this rotating around. With these sections here, you're going to have a brush that is up against here, another one on this other side. As this section, or this sector, makes contact, it's going to make poor contact, good contact, poor contact, and then lose contact. You have current flowing through there, the magnetic field is going to expand out, and then the magnetic field is going to collapse back down. As the magnetic field expands out and collapses down multiple times per second, it induces a voltage into itself and into the other windings in here. So there's all kinds of electromagnetic interference going on inside of the motor. The faster the motor spins, the more electromagnetic interference there is. Inside of the motor, that electromagnetic interference is your resistance. Faster it spins, the more resistance it's going to have, so it's going to reach a certain RPM and it's going to hold there. The reason I explain that to you is if you get a low voltage coming into here, the motor's going to turn slower. If the motor turns slower, there's less resistance in the motor, so even though you have less voltage, you'll actually have more current flowing through there, and you can burn up a motor with a low voltage. If you have a 12-volt motor and you put 6 volts to it, you're in danger of burning up the motor, which is backwards from anything else, but that's how DC motors work. The other thing that you'll come across, and not so much with the starter motor, because hopefully you never stall the starter motor, a power window motor, when you push the button to roll the window up or roll the window down, when it gets to the end of its travel, the motor stalls. Now if you continue to hold that switch over there, it's going to burn up the motor. Where these contacts are, current's just going to flow through there. It's not moving, so there's no electromagnetic fields. This is just going to get hotter and you'll burn the motor out. And I've pulled them apart and seen where brushes are burned about 180 degrees off from each other, and that's what happened. Somebody stalled it and just kept the switch over there. If you hear the term of low voltage burnout on a motor, that's the reason why. It needs those electromagnetic fields. It's going to get those with the faster it turns. Starter drive. This is the part that's going to actually engage the ring gear, and you can see down here, well, this is not the right pinion gear for this ring gear, but you can see how they're going to match up. Pinion gear, this part here is a overrunning clutch, which is this part here, and this one here is what's going to push the pinion gear. I'm going to go back to slide 1, slide 2. Here's our plunger. This plunger is going to be drawn in by the electromagnet. As this gets drawn in, this shift lever right here, it's going to pivot at this point. This is going to move that direction. This is going to move that direction, and that's what's going to engage our pinion gear to the ring gear. A few things that are going on here. This spring right here, which you can't see on this one, when this gets pushed out there, if this tooth right here was lined up exactly with the tooth on the pinion gear, it's not going to engage. And they would just hit, starter wouldn't work. What they're going to do is, if that happens, that's going to compress this spring. As soon as the starter motor turns just a little bit, that spring is going to push the pinion gear out, and now you'll crank the engine, start the engine. The reason for the overrunning clutch, we don't want the engine to turn the starter motor. We want the starter motor to turn the engine, but not the other way around. This ring gear is going to be about a 10-to-1, 15-to-1 gear ratio. If we're at a 10-to-1 gear ratio, as soon as you start the car, it's going to take the car about a second or so to get up to 1,000 RPM. If the ring gear is turning at 1,000 RPM and this pinion gear is still engaged, that means this armature is spinning at 10,000 RPM. And this armature will not handle 10,000 RPM. The sectors of the commutator are pretty much glued in there with a plastic type substance. These are going to fly apart. They're going to break these brushes inside of there, and your motor is destroyed. Pinion gear to engage the ring gear, overrunning clutch to prevent the engine from turning the starter motor, this spring to allow it to not be lined up when it goes to engage. The other term that you're going to hear for a starter drive is the term Bendix. People will call this a Bendix drive. I put a picture over here of an actual Bendix drive. Bendix drive was used on starters prior to having the solenoid actuated. On this system here, this gear will sit back over here, turn the starter over, these threads are reversed, and centrifugal force is going to throw this pinion gear out to engage the ring gear. Now that it's engaged the ring gear, it's going to crank the engine over. When the engine starts, the centrifugal force is going to work the opposite direction and kick this out. So it was actually a mechanical overrunning clutch on that. And hopefully you would let your foot off the starter by that time. This is an actual Bendix drive. This right here is not. But you can go to any parts store, you can ask them For a Bendix drive, given the make, model, and year, they'll get you one of these. So these are generically referred to as a Bendix drive. Technically, they're not. They're a starter drive, pinion drive, overrunning clutch. The ring gear, the engine doesn't randomly stop. Where the engine is going to stop at is on a compression stroke. So on a 6-cylinder engine, it'll stop in one of 3 places. On a 8-cylinder engine, it'll stop at one of 4 places. Because it always tends to stop in the same place on a compression stroke, when the pinion gear goes to engage, you can see right here, this is the compression stroke. This is where that teeth got worn out. You can see down here, this is the new ring gear. Here's the old one. And this is a little bit deceptive because this is actually worn out a little over 25% of it. And when we put a new starter on there, the starter motor would grind, and that was the pinion gear just spinning against these teeth. It wasn't engaging. Ended up having to pull the starter motor back out, see the damage on here, and replace the ring gear. When you replace the starter motor, you should look up inside there, turn the engine, check to make sure the ring gear is in good condition. Not very often the ring gears wear out, but it's definitely worth looking because you don't get paid for doing the job a second time. Starter solenoid. Here's our plunger. This is a little bit deceptive. There's a plate right here which is part of this plunger assembly, so this spring is actually pushing the plunger that direction. When battery voltage is applied to the electromagnet, this plunger is going to be drawn in here. It is going to push the pinion gear out to here where it engages the ring gear. After the pinion gear engages the ring gear, then these contacts are going to close on this disc here. Here you can see the shift lever. It's going to push the pinion gear up inside the nose cone, and I've got this sitting next to it. This part right here is going to go inside of this bushing. Some starters had bearings on there. A lot of them had bushings. And this is going to get pushed up, so right inside here, and that's where your ring gear is going to be. This contact is not going to close until after the pinion gear engages, unless there's something broken about this lever. Starter solenoid is going to do 2 things. First of all, it is going to engage the pinion gear. Second, it's going to close the contacts for the relay. This terminal right here is going to be your battery terminal. This one is your motor terminal. This disc is going to close the contact between those two. On the starter solenoid, this is your wear item. When you go to start the engine and you hear the solenoid click, that means your pinion gear came out engaged, and it engages loud. You hear the click, but then it doesn't crank. It seems odd that the solenoid worked, but the motor doesn't. The reason the motor doesn't work is because the contacts in the solenoid are burnt out. And I forgot to talk about this. The brushes, this is your major wear item. As the commutator turns inside of here, the arcing, the electromagnetic fields, building up, coming down, as this turns, it's going to constantly be arcing. Your commutator is going to get scarred, and these brushes will wear. The shorter the brushes get, the less spring tension there is on there. It's going to eventually get to the point where it doesn't ground. And this is the one where you hear people talk about they turn the key to the start position and nothing happens, and somebody says, hey, take a hammer and beat on it. And it's not magic, because you hit it with a hammer, the brushes get jarred around, and they make contact again, and now it'll work for a little while. If that worked, you still need to replace the starter motor because you're not going to be able to do that very many times before it just won't work at all. The motor, brushes are going to be the most common part to wear out. On the solenoid, it's this disc inside here that's going to wear out. Inside of the starter solenoid, there's 2 windings. There's a pull-in winding and a hold-in winding. We have 3 terminals on here. S, B, and M terminal. Here's your solenoid. This is going to be your battery terminal. Your positive battery cable is going to come to there. This terminal here connects directly to the motor. And this one is your S terminal, which is going to come from the ignition switch, the safety switch. This S terminal, so you turn the key to the start position, you have it in park or neutral, or you have the clutch depressed, and that's going to put battery voltage here. The hold-in winding grounds at the housing. This housing right here is going to be volted to the starter motor. The starter motor is volted to the engine. That's ground. If you want to check the hold-in winding, you're going to use an ohm meter. You're going to check from here to the housing, and you're going to be able to measure the resistance of the hold-in winding. You can also take battery voltage, connect it up here, ground there, stick the plunger inside there with that spring, it won't pull the spring in, but if you push the spring in by hand, it'll hold it. That'll tell you that the hold-in winding is good. The pull-in winding comes from the S terminal to the M terminal. By looking at this, you look at this bolt here and this bolt here, and there's not much difference between the M terminal and the battery terminal. However, looking at this right here, two windings coming inside of here, the hold-in winding comes out. That's what's soldered to this piece, this metal piece right here, and comes to the motor terminal. This is what's going to identify the motor terminal. Once you know which one is the motor terminal, this is the battery terminal. If you pull the starter motor apart and you start looking at it, it's like, wait, this will go in two ways. Which way does it go in? You need to remember that this part right here goes to the motor. Reason for the two separate windings. This spring here is pretty strong, and you got a lot of weight this is going to move, so this is a really large solenoid, one of the largest solenoids we have on the car. There's no soft iron core inside of here, so we need a really strong magnetic field to pull this in. And that's true with any solenoid. However, once this gets pulled in, this plunger now becomes a soft iron core, meaning it's going to make the electromagnetic field a lot stronger. So we can use a weak magnetic field to hold it in, but we need a strong magnetic field to pull it in. I tested this on an older car. This was a starter motor off of a V8. And I measured the current on this S terminal with the hold-in and the pull-in winding. That vehicle drew 70 amps just through the solenoid. We need to save that amperage for the starter motor. That's the reason that this pull-in winding's here. Now let's take a look at what's going to happen. Let me erase the ink that's on here. Turn the key to the start position. We're going to have battery voltage here. We have ground here and ground through the motor for the pull-in winding. The motor, again, I talked earlier that if you check the resistance on a motor, you will find like 1/10 of an ohm resistance. The reason you'll find 1/10 is because on a lot of ohm meters, that's the lowest reading that you're going to get. There's actually very little resistance in the motor while it is stationary. Both the pull-in and the hold-in winding go to ground. The plunger is going to get pulled in, and it's just a matter of milliseconds that the plunger is going to get pulled in. When the plunger gets pulled in from our battery terminal, we're now going to put full battery voltage here. This is that disc here. It's a large, heavy disc that's going to provide that. We're going to put from the battery cable battery voltage right to the motor terminal. I have battery voltage here. Once the plunger closes, I'm going to have battery voltage here, meaning it's going to push this direction. This is going to push this direction. I'm using opposing voltage to shut the pull-in winding off. All solenoids can be designed this way, but they're only going to design this one this way because they want to save that amperage for the motor. But one more time, the reason for the pull-in winding is so that we save the amperage for the motor. And the reason I repeated that is just in case you were to come across that question on a quiz. Newer ignition switches, we have 4 positions, going to be off, accessory, run, and start. This is an older switch that had 6 positions. They had an accessory, lock, off, run. The bulb test and start were actually the same thing. Taking a look at this one, we have our off position here. Turn it to a first position accessory. If you turn the key to the accessory position or the off position, you let go of the key, it'll stay right there. There's a detent. And this is what we're talking about. The detent is what holds it there. Visualize a ball bearing, and there's a groove. Then there's a spring pushing this ball bearing. It comes over here, the ball bearing is going to drop in that groove, and that's going to hold it in that spot right there. Off, accessory, run. You let go of the key, it stays right there. Those have a detent. Of the start position, which is a momentary contact. This right here, steering column is going to go inside of here. This is where your key goes in, so this is your lock cylinder, and the ignition switch is down on this end. This is the same item photographed from the other angle. This black part right here is your ignition switch. The reason I show you this clamp right here, which is this metal piece right there, has this bolt. When you look at that bolt on the car, there's no way to grab a hold of that bolt. This is what they call a breakaway bolt. To get it off, you're going to have to put a groove in there. So cut it, use a chisel or something to put a groove in there, then get a screwdriver and turn it off. When you go to put it in, you buy a new breakaway bolt. This will have a head right here. You turn it down, when the head snaps off, it's torqued down to where it's supposed to be. It'll stay there. This is designed to make it tamper resistant, harder for somebody to steal the vehicle. If you have a manual transmission, it is going to be a normally open switch. Push the clutch pedal to the floor, and that will close the switch, and now you can crank the engine. This is typical of what a clutch safety switch will look like. Again, it's open inside of here. When you push the clutch pedal down, it's going to push this contact in, closing the contacts inside of here, crank the engine. This one here is a safety switch for an automatic transmission. They're showing you here, it is closed in park, closed in neutral. When they draw it on the wiring diagram, they would draw it as normally closed, because when car at rest, you're in park. This one is mounted on the transmission. That's the reason it's so dirty. On some of these, when you install them, there is a alignment pin, goes in, and it's adjusted. Others of them, this elongated hole, you have to go through a specific adjustment procedure when you install it. On some of the manual transmissions, when you install this, it'll automatically adjust as you put it on. Others, the reason this is so long is you have to adjust it once you get it on. Whether the vehicle you're working on is adjustable or non-adjustable, you need to look in the service manual and follow the procedure. Some of them are really simple to adjust. Others, they get complicated. That ends the starter, so hopefully you understand what each of the components are and what's happening with the starter system.